Okay, so our first test with some power measurements in and out with our 3 battery setup. Here we have the 2 in series to give us our 24 volts. We have our 12 volt receiving battery or charging battery, and we have our inverter 500 watts, and we have our watt meter here. I've plugged this straight into 240 volts with this globe to check how accurate it is from our inverter, being a modified sine wave inverter, and it is pretty much well spot on. So we don't have to worry about the meter here being fooled by a sine wave that's not quite a sine, but it's very close to with these new inverters. And of course our load is a pure resistive load, so the meter will not have to also cope with inductive loads or anything like that. So that meter there is going to be fairly accurate. Our meter we're using to read the current going through the system is one of those meters I use all the time, because I found that those specific meters are very good at averaging out current on spiky loads, which we do have on the input of the sine wave inverter, which is not a pure sine wave inverter, it's a modified one, but nonetheless it is very close. And it's just started raining. Chad will love that. That is the voltage across our receiving battery or charging battery. Sorry about the rain, can't do anything about that. And this one here is the voltage across our 24 volt supply. Okay, so what we're going to be doing here is calculating our power in, which is the power out from the 24 volts, the power out from the inverter, which will be what's being delivered to the globe here, or dissipated by the globe, and our power out as in charging battery 3. We only need the one single current measurement, because that will apply to our system as a whole, and the output from the inverter, our watt meter here, is taken care of. I can't believe it started raining as soon as I want to do this. It happens all the time. Okay, so we're going to plug our load in. And our inverter doesn't like that for some reason. Maybe something to do with the battery being a bit high in voltage. I'm really not sure why it's doing that. Because a standard automobile will charge a battery to 13.4, this should go to about 14.6 before it starts having a hissy fit. And the fault light hasn't come up. I don't know what's going on there. Nonetheless, 24.66 volts. I'm at 2.912 amps. 2.9 2.911, so it's close enough to 2.91. The voltage across our charge battery is 13.5. And that inverter should be happy with that, but it's not. And we are delivering 21.8 watts to our globe there. So that battery's not being charged very hard. It's only giving 2.9 amps, which is well below the C20 rate. I don't know why that is making noise. It wasn't before. It is now. But anyway, we do have some numbers to start with. I'm going to sort that inverter out, see what's going on with it. Those are the numbers we have. So now we can see how close this lot here leads up to our input, and get a starting, turn that noise off, and get a starting point for our testing here. But there is no way that inverter should be making such a noise. What I will do is I'm just going to disconnect all this for a moment. And hook our inverter up. A little bit here, that's the voltage. Hook our inverter up just to the battery. And we can see that it is quite fine. It's no longer making any noise. So what I might do is I'll try and swap this position of the inverter around and put it between positive rails of our 24 volt and 12 volt, see if that makes any difference. So I'll be back shortly and we'll see how we go. Okay, so I swapped the inverter and battery 3 position around, made no difference. We have the same problem, but we have worked out what the problem is. This new meter I've put in here is reading the voltage across our inverter, or what our inverter is running on. If we switch it back on, it's okay for a little while until that battery 3 there reaches 13.2 volts. Right there. And we can now see the potential difference between our charge battery and our 2 run batteries is only 10.9 volts, which means that our inverter is having a hissy fit because it's on low voltage. There's a low voltage alarm. So we're going to have to rectify that problem. I'll have to discharge that battery a little more. Like I said, they're new batteries, they're very healthy, so they're going to take a charge really good, and we're going to run into this problem of the potential difference closing too fast or dropping too fast. There are ways I can fix that, and that's going to involve some more meters and a load on our 3rd battery. But what we're actually looking for is this so-called globe here being run for free, and regardless of our little alarm there, we can still we're still able to obtain some measurements. And what we haven't measured is the idle consumption of our inverter. But we'll have to get into that one a little later. That's going to require a little more accurate measurement. So, but what we're going to do now, work out these numbers, And I'm also going to just run this inverter straight off one of the batteries, and we'll also write down our power in and power out in standard configuration and see how it compares with the 3 battery situation here. So that will also take into account losses in the inverter itself. They will be in both measurements, so it'll be a fair and square deal between the two. Alright, so I'm going to go and do that now, and we'll be back when I'm set up. Alright, so at the moment we're just running the inverter straight off one of the 12 volt batteries. This was battery 3. I'm going to pull that down pretty hard so as we can get a longer run time next time. That is our power in, 2.924 amps at 11.9 volts, which we're going to do here. And our power out is 23.3 watts. So we're simply going to compare the 3 battery setup with the single battery setup and see which one is more efficient of the two to start with. In the next video I'm going to sort out this 3rd battery charging up too fast. I simply may just place another resistive load across that battery to keep it down, which we can also calculate the power out for, so no problem there at all. But the battery did charge up pretty quick and didn't give us much time to sort things out very accurately, but regardless we were still able to get a ballpark figure of what we're going to be looking at between the 2 setups. So they are all the numbers there, you guys can crunch them yourself. The top one here, those 3 of course being our 3 battery setup, and these 2 here being our single battery setup. I'll go crunch the numbers now and we'll come back and have a look at them. Okay, so our results are in. The 3 battery setup, the input power is 71.76 watts. That's what is being delivered by our 24 volt battery bank. Our total power out equaled 61.08 watts, or 0.85 watts, and that gives us an efficiency of 85.12%. So you may think that's pretty average, but if we look at the next numbers, single battery setup, as we have running here right now, pulling that battery down a bit more, our power in was 34.748 watts, our power out is 23.3 watts, and our efficiency is 67.05%. That means the other 33% that is missing here from our light bulb is being dissipated by the inverter itself in the way of heat, and that would equal our 33 watts we're missing from this number here. The interesting part is we are only 15 odd watts, or 15 odd percent short of being 100% efficient, and that 85.12% does not include that 33% of the power being dissipated by the inverter itself. So if we have an efficiency of 85.12%, discounting the energy being dissipated by the inverter itself, where that inverter is dissipating 33% of the energy, things start to get a little interesting. So this definitely warrants further investigation, this 3 battery setup, and we need to calculate each and every component a little more accurately, and we can get much more accurate figures. These are just ballpark figures from our first test. This one here is going to be accurate, of course, because that is what it is now. 23.2%, 2.874 amps at 11.5, 11.6 volts. So a 67% efficiency with this setup is all we're getting from our inverter. So that makes these numbers here very interesting indeed. So I'm going to discharge this third battery a lot more, so it gives us a little more run time. I'm also going to place a load on that battery to keep it down while we were running the test, and so our potential difference doesn't drop so fast. But I have to admit, at the moment, that is very interesting as to why our efficiency went up so much in the 3 battery system compared to the single battery running the inverter, which is not what I expected to see. I expected to see more losses due to having more batteries in the system, but for some reason that is not the case. We have more losses with the single battery running the exact same unit, the exact same load. That load before was 21.8 watts because our inverter was only seeing about 10.6 odd volts or something like that, whereas where our inverter sees 11.5 volts, our efficiency dropped down, but the power out was still very close, 23.3 watts compared to 21.8 watts. So you're only looking at about 1.5 watts difference on the output, but for some reason the efficiency died in the arse. Okay, we're going to keep going with this because like I said, this result here is not what I expected. I expected this one to be much lower than this one, but it is not. This one is much higher than this one for some reason. So I might have missed something here, but this, when you're calculating simply using volts times amps, and you're using the very same watt meter, reading the same waveform from the inverter, driving the same load, you would expect that meter to be very close to extremely accurate to what it's telling you. Yeah, we're going to look into this a little deeper, because that 33% that is missing there, being dissipated by the inverter, is more than the 15% we are missing here. Thanks for watching, guys. Stay tuned, this is getting interesting. Cheers.